so in the previous class we have discussed if the solid, for example, we have discussed in the previous class if the solid is changing into liquid. Solid is changing into liquid. Let's say the solid we have ice, and let's say it is at 0°C and it changed into liquid. For example, this liquid is water. Ice become water. And the temperature of this liquid is also 0°C. So we have to supply a certain amount of heat actually. So that heat, we have to supply heat. Okay, so that heat what we will supply actually, that will not increase the temperature, because if the phase is changing, you can see the phase is changing, means the solid is changing into liquid. If the phase is changing, it means that potential energy changes. Potential energy changes. So this is one thing you need to understand. The second thing you need to understand is that kinetic energy does not change. If the phase is changing, kinetic energy does not change. So kinetic energy does not change. So you have to be very clear about this. So when the phase is changing, kinetic energy does not change, but potential energy changes, because when the solid is changing into liquid, we have to supply heat, and that heat we supply, or that thermal energy we supply, that thermal energy will be used to increase the potential energy of molecules. Okay, potential energy of molecules. So we can also say that the increases potential energy of molecules, or we can also say that, for example, this heat what I will supply, what this will do, this will use to separate the molecules. So this heat will be used to separate molecules. So this thermal energy we supply will be used to separate molecules. And for example, if the liquid is changing into gas, we see in case of liquid, for example, the molecules are close together, but in case of gas, for example, molecules far away from each other. So these molecules go away from each other because they have potential energy. So they have more potential energy, so they go away from each other. Okay, so this thing we have to be very clear. When the phase is changing, kinetic energy does not change, only potential energy change. If we supply heat, it means a potential energy will increase. If it is also like this, if the liquid change back into solid, in this case heat will be released. So we will say the thermal energy will be released. So these things we have to be very clear. So when solid change into liquid, potential energy will increase, we have to supply heat. But when liquid change, okay, PE is the potential energy, please. So the PE, what I'm saying is that this is potential energy. Okay, so this is PE. So this is potential energy. Okay, so this is, please, we need to understand, this is potential energy, this is PE. Okay, so the separation between molecules increase, it means the potential energy increases. Okay, so this is what we need to understand. Okay, so this point is clear. So this is what we have covered in the previous class. So now today's class we will talk about. Okay, so today's class, our focus is when the liquid is changing into gas. For example, we have a liquid, so we will discuss about this one. If the liquid is changing into gas, so liquid, for example, we have a water, and when the water change into, so we can simply say that when the water it change into steam, means gas. Okay, change into steam. So let's say this liquid is at 100 degrees Celsius and it become a gas at 100 degrees Celsius as well. So that time we need to supply thermal energy. So we have to supply thermal energy. Okay, again, why we need to supply thermal energy? If the liquid at 100 degrees Celsius is changing into gas at 100 degrees Celsius, because we need to do work to separate molecules. We need to do work actually. We need to do work to separate molecules, because we understand molecules in liquid, they are close together, but molecules in gas, they are far away from each other. So we have to do work to separate molecules. So why we need to supply thermal energy? Because we need to do work to separate molecules. So this one, please, you have to understand, is this point is clear? Why do we need to supply thermal energy? One reason you can say is phase is changing. So one way, the simple way to say is that because phase is changing. And other way to say this one is, you can say because work has to be done to separate molecules. Okay, so this is the main idea what we need to understand. So if you look at these solid to liquid and liquid to gas, they are almost similar. Okay, almost similar. So now if the gas, for example, gas change into liquid, so this is what we call condensation actually. So in this case, energy will be released. Okay, energy will be released. But when liquid change into gas, energy we have to supply. So in this case, it will be released. So we will say energy will be released. That in this case, we have to supply because the separation between molecules will increase. Okay, so these are the main ideas we need to understand. So any question about this one, please? Okay, look at this one. Is this point is clear to you? Okay, so this is what we need to understand. So if this is okay, so I will clean this one and I will explain you what is specific latent heat of vaporization. Okay, excellent. Okay, here, excellent. Now please, you can see now. Okay, so the next thing, excellent. So the next thing we need to understand is that now you can see here now it will give you better understanding. Now you can see we have, okay, this one please. Now you can see we have liquid. Okay, excellent, excellent. Now you can see we have liquid here. This one you can see we have liquid. These are liquid molecules. They are close together. That if we want liquid to become a gas at the same temperature, for example, this liquid if we say is a water, so this water is at 100 degrees Celsius. We want this one to become a gas, or we can say this become a steam, and we want this steam temperature also 100 degrees Celsius. So in this case you can see here the temperature is not changing, so we will say the kinetic energy here is the same. So we will say kinetic energy, I can say kinetic energy 1 and this is kinetic energy 2. So you will simply say that kinetic energy 1 is equal to kinetic energy 2, means that kinetic energy of molecule, average kinetic energy of molecules is same because temperature is the same. But what is the difference? But still when liquid change into gas, we have to supply thermal energy, or simply we can say that we have to supply heat. So thermal energy is a proper way to say actually. We need to supply thermal energy. So what this energy will do? This energy will do work actually and separate these molecules. Okay, so we will say that, let's say the potential energy of molecules here is P1 and let's say the potential energy here is equal to P2. So in this case you will say that P2 has to be greater than PE1 because we did work and that work is used to increase the potential energy of these molecules. Okay, so this is what we need to understand. Okay, the formula is the same. So formula as we have discussed before. So Q is equal to M L V. So I will discuss V later. So now when the liquid is changing into gas, the amount of heat supplied to increase temperature of 1 kg, we call that is specific latent heat of vaporization. So this vapor form, so we call vaporization. So it's similar to the specific heat of fusion, specific latent heat of fusion, but only difference is that phase is different. So you can see the specific latent heat of vaporization is the amount of heat energy required to convert unit mass liquid into vapor without, this is very important thing, that's the reason I'm saying again, without change in temperature. So we call is a latent. This latent means that hidden actually. Latent means hidden. Latent means hidden. We don't see the change in temperature, but still we need to supply thermal energy. So we give name latent because temperature does not change. Okay, so this V, for example, V is for vaporization. So the V is for vaporization. So that's the reason we're using this small V here. So this is for vaporization. So again, now you will say that Q is the heat supplied. This can be the heat supplied or released. So Q can be the heat supplied or Q can be the heat released. It depends how phase is changing. M again, the mass. M is the mass. So boiled off, how much water has been boiled off? So we also have to be very clear. Next example, I will explain what does it mean mass boiled off. So this is the specific latent heat of vaporization. Specific. So they are different. Latent heat of fusion and latent heat of vaporization, they are different. When the liquid change into gas, you have to use specific latent heat of vaporization, but solid change into liquid, you have to use specific latent heat of fusion. So this is specific latent heat of vaporization. So we will simply say that this is specific latent heat of vaporization. So I hope this is clear to you. So let's move on to next one. Okay, we have discussed a lot about this. Okay, next one now, please. Now you can see here. So this one now you can see. This gas, for example, we have this gas or we have this vapor. And this vapor is at 100 degrees Celsius and we form liquid. This liquid is also at 100 degrees Celsius. Now if this change back means the gas change into liquid now. In this case, heat will be released because kinetic energy of molecules will not change, but potential energy of molecules will decrease. It means heat has to be released. So in this case, heat will be released. Okay, so this is. Okay, so you can also see here, if you have 1 kg of vapor, it change into 1 kg of liquid at 100 degrees Celsius, it will release this much heat. This much thermal energy will be released. 2260 kilojoules. If 1 kilogram steam change back into liquid. Okay, so this number is important. So we need to understand what is specific latent heat of vaporization. Okay, temperature has to be the same. So this is the key point. Okay. Okay, so if this is okay, so we can move on to next one. Okay, next one please. Here you can see now. This is the formula. Formula is the same. Q is equal to ml. The specific latent heat of vaporization of water, this number is important, you need to understand. So is equal to this one. So this is here. Okay, so we can also write down this one. This is 2.3 times 10 to 6 joules per kg. Joules per kg. So it means if we have a liquid, for example, let's say this is a 1 kg liquid, and let's say this is at 100 degrees Celsius, we change into, this is liquid, and we change into gas or steam, we can say, this is 1 kg. So this is water. So this liquid is water. So you have to be clear what is this. And this become steam. So this is steam. If this change into this one, we have to supply heat. Thermal energy. That thermal energy has to be equal to 2.3 times 10 to 6 joules. Okay, this much thermal energy we have to supply, because this number is telling us if you have 1 kg liquid at 100 degrees Celsius and you change into steam of 1 kg at 100 degrees Celsius, the amount of heat we need, that is this much. And this is the specific latent heat of water. Okay, vaporization of water. This is the Q, this one please, this one E, you can write down Q, or you can say E. So this is actually heat supplied. It can be heat supplied. It can be heat supplied. Or this also can be heat released. Okay, it also can be heat released. It depends how the phase is changing. Okay, Q and E, they are the same. Okay, so I hope this is clear to you. Okay, so if this is clear, so we can move on to next one. Okay, so let's go to next one now. Okay, here please. Now here is experiment. This, okay, excellent. Now here is experiment now. This will help you to understand this more in detail. Okay, this will help you to understand more in detail. Okay, excellent. Let's say this is 100. I will make this number simple so we can do simple calculations. Let's say this number is 1. I will say this is 0. Let's say this is 100 gram of water. Okay, this is 100 gram of water now, and this is at 100 degrees Celsius. Let's say we have water that is at 100 degrees Celsius, and the mass of the water, you can see the mass of the water is 100 gram. This is, let's say, at T is equal to, let me write down here for you, at T is equal to, I will say at T is equal to 0 second. We have 100 gram of water. So this is boiling water, and this is at 100 degrees Celsius. Let's say after T is equal to 5, I can say after T is equal to 5 seconds, or you can say 5 minutes, let's say 5 minutes. This is T is equal to 0 second. Here I can say T is equal to 5 minutes. Otherwise, I can also use the simple number. I can use the same units. I can say, let's say this is equal after 50 seconds. Now, the mass here become, let's say 60 gram now. But this is still at 100 degrees Celsius. So these two numbers I want you to understand. First of all, you can see here we have boiling water that is at 100 degrees Celsius, and its mass is given, that is 100 gram when time is 0, and temperature is this one. But after 50 seconds, its mass is 60 kg now, and its temperature is still 100 degrees Celsius. Now this heater, for example, this heater, I can say the power of the heater, I can say, we will do this one question together. let's say the power of this heater, let's say this is equal to 10 watts. Okay, is equal to 10 watts. Now we need to find what is specific latent heat of this liquid or water. So what we will do, we will simply say Q has to be equal to ml. Okay, Q has to be equal to small m times L. So the Q you can find out, Q you will say this is P times time, power times time, and here is a m. We have to understand how to find this m, and this L we need to find. So we can simply say L has to be equal to P times time, power times time divided by m. So how we can find here? Let me write down the numbers for you. P is equal to 10 and the time we have is 50 seconds divided by. So we need to find M. So the M, please, you need to understand the delta M. I can also say that how much water has been boiled away. So M is how much water boiled away. How much water boiled away. So that you have to find out. Now we have 600 we have at the beginning. Now we left with 60. So how much has been boiled away? You will say 100 minus 60. Excellent. So you will simply say it has to be 40 gram. So you will use 40 gram here. Okay, so you have to convert into kgs now. So the 40 gram you will say this is 0.040 kg. So you will use here 0.040 kg. So you have to be clear what is this M. Okay, not only the mass of the liquid, but this is the mass of the water boiled away. So you have to be clear about this one. Okay, so this one please, then we can say this is 0.040. So that's all, then we can find our final answer. Okay, so this is how this experiment is done. So first of all, this water has to be at 100 degrees Celsius. If this is not at 100 degrees Celsius, so what we will do? So for example, we have liquid here. Let's say this is at 20 degrees Celsius. Let's say this is a liquid inside we have, and this liquid is at 20 degrees Celsius. We will supply heat to this one. When its temperature become 100 degrees Celsius, then we will start our stopwatch. Okay, when it is at 100 degrees Celsius, we will find how much mass of water is here and we will start our stopwatch and we will find the time. Okay, not when it is at 20 degrees Celsius. You have to start your stopwatch. Start your stopwatch. So you have to understand. Start stopwatch when temperature is equal to 100 degrees Celsius. And then that time you can use here. Okay, so I hope this is very clear. So you can also look at this example now. So this is the power of the heater is given, and this heater has been switched on for 500 seconds, and this much water has been boiled away. So then we can use the formula and we can find out. Okay, so this is how we can find out. So is this one is clear? Okay, so this is main thing we have to understand. If you have any questions, you can ask me right now. If it is clear, we will go to next then. Excellent. So let's go to next one now. Okay, so this is what you need to, main thing is the mass actually. Mass is the main thing. Okay, so you have to be clear about that. Okay, now please here. Now you need to understand this is very important now. So we have studied until now a lot about specific heat capacity. We also have discussed about latent heat. Okay, so now we will combine here now. So first thing you need to understand the specific. Excellent. So here please, specific heat capacity we have discussed. Specific heat capacity. Okay, so we have discussed specific heat capacity. Specific heat capacity, we have found that Q is equal to mc delta T. We have used this one. And also we have discussed now specific latent heat. So we have discussed specific latent heat right now. So we can write down specific latent heat. So the Q is equal to M times L. So this one, when you will use this formula, so first thing, temperature is changing. If there is delta T is 0, of course this will be 0. So you need to understand, you will use this formula when temperature changes. If the temperature is changing, otherwise specific heat capacity will be 0. And no phase change. So you will use when no phase, no change in phase, or we can say no phase change. So no change in phase. So you will use this formula that time. So you have to understand this one. And this one, when we will use, do you see any change in temperature here? No, we are not talking about change in temperature here. So this formula only you will use when the phase change, when the phase is changing. Okay, so this you have to understand. Now, for example, if I need to understand how much heat is supplied in this region, I will simply say I have to use formula Q is equal to ml, because temperature is not changing, phase is changing. So here, which formula I have to use? You see the temperature is changing because on y-axis we have temperature. So temperature is changing, we have to use mc delta T. And here again we see the temperature is changing, we have to use Q is equal to mc delta T. So here the phase is changing, we have to use Q is equal to ml. And now you see at this point temperature is changing, we have to use Q is equal to mc delta T. So this is a whole picture of changes of state. Okay, so when to use specific heat capacity and when to use specific latent heat. So you have to be very clear about this. Okay, I hope this is clear to you. I will also send you in summary notes. So let's move on to next one. Okay, here please. Here are few questions for you to answer. So here please, there are two questions for you. First of all, think about this one and try to figure out your own answer, and then I will show you answer. So you have 2 minutes. So just think about this one, how you will answer. Okay, so let me show you answers now. Okay, here please. If you are thinking like this, that's wonderful. Okay, now let me give you one simple question more now. So little bit maybe tricky question, but I hope you will be able to answer now. So that is the reason. Now let's say we have 2 glass of water. Let's say this is a 1 glass of water. This is 1 glass of water. Okay, and this glass of water, let's say, is at, okay, that's good. So let me ask you one question. So here, so let's say we have 1 glass of water. This is at 20 degrees Celsius. And let's say we have an other glass of water. This one, let's say, is at 0 degrees Celsius. So I can say this is at 0 degrees Celsius. So I will just draw a line here for you. And you also have ice. So this is ice. So this is ice, and this is also at 0 degree Celsius. Or I can say 0 degree Celsius, make it just simple. It is at 0 degree Celsius now. So you have two options. So we have two options. I will write down here two options. To cool down water, to cool down this water, to cool down water. One option is you have water. This is cold water. This is at 0 degrees Celsius, and this is ice that is at 0 degrees Celsius. So one option is that you have this glass of water. Let me change the color. Let's say this is water. This water is different. Let's say just color for better understanding. And let's say this ice color is like this one. So you have two options now. You can add this water into this one. So we can do like this. So one option, you can add water here. And the second option, what you can do is, so we have, this is second option. We add ice here now. Ice. So which one will cool down more actually? Ice or cold water? Okay, so which will cool down this water more? Cold water or ice? Let's say this is one A, this is B. So which one will cool down more? Ice or ice? Excellent. Why? So why ice will cool down more actually? And the reason is that, first of all, you need to understand ice has to change. Ice, the reason is that ice has to change into liquid. Okay, excellent. Ice has to change into liquid first of all. So it will take heat. To change into liquid, it will absorb heat from the water. Then this liquid change into an other liquid at some temperature. So because ice need energy to change its phase. High specific latent heat, are you can simply say in that way, but also you need to understand is that if we simply add water, they will reach one equilibrium temperature. But if we add ice, first of all, ice will change into liquid. This liquid will be 0 degrees Celsius. Then this will change to an other temperature. So you see, this is the extra amount of energy it will take from the surrounding water. So ice will lower temperature more. So ice will lower temperature more. So this is one thing you need to understand. That's the reason ice is good. It will lower temperature more. So this is what we can say. That's the reason in cold drinks actually we use ice. We don't use cold water because cold water will not lower temperature. It will just decrease temperature by a small amount. But ice will increase by higher amount because it need energy to change phase as well. Or you can say ice has high specific latent heat of fusion. So this thing we have to understand. Okay, let's go to next one now. So here is another question for you. So here please look at this question now and try to answer. Okay, so let me clean for you so you can see the question clear. So let me clean this part. So this is not directly from this topic, but this is from thermal physics. Okay, so first of all, read question and think about this one, how you will answer. Okay, so if you have think about this question now, so let me explain to you now. First of all, let me show you the answer. Okay, here please. Yes, higher C, that is one reason, but other reason for this one is that water will evaporate. Okay, so water with high energy molecules will leave actually. So the rest of the water temperature will go down. Okay, because evaporation will take place and temperature of water will go down. Okay, so this is actually from evaporation topic. Okay, evaporation is a cooling process. So we will say evaporation is a cooling process. So the water will cool down more. Okay, because some high energy molecules of water, they will evaporate. So when they will leave the liquid, they will take energy away from the liquid. So its temperature will go down. So the temperature of remaining liquid will go down. Okay, is this point is okay? Okay, because high energy molecules will leave the liquid, so its temperature will go down. Okay, so this is please you need to understand. Okay, let's go to next one now. Okay, next one we will talk about, this is the last topic in thermal physics. Okay, excellent. So excellent. So this is the last topic in thermal physics. So we will talk about only about conduction. We need to understand what is conduction and what is convection and what is radiation. So these are the three ways actually we can transfer energy. Means we can transfer thermal energy from one place to another place by conduction, by convection, or by radiation. Okay, so before I start this chapter, you need to understand is that as water, for example, water flow from high level to low level, means water fall from high level to low level. Energy flow from high temperature to low temperature, means energy always flow from cold to hot to cold object. So you can see, so thermal energy flow only. So the thermal energy flow, so this is one thing you have to clear, but this is from our common sense as well. Thermal energy always flow from hot object, means from high temperature to cold or low temperature. Hot means high temperature, higher temperature. So this means higher temperature. If two objects, they have different temperature, one is at a higher temperature, other one is at lower, the higher temperature body will give energy to cold one. So from higher temperature to lower temperature. Okay, so this is first thing we have to understand. So next we will focus on conduction. So next thing we will focus on conduction. Then from conduction we will go to convection and then we go to radiation. So these three ways of heat transfer we need to understand. Okay, before I explain to you conduction, so let's look at this animation now. Look at this animation please. Watch animation. Okay, so as you have seen from here, for example, at this point the color is changing. You see the color was changing. So the color changing means that the heat is flowing. This end is the hot end and this end is the cold end. If we continue supplying heat, heat will flow from hot to cold. And conduction, please. Conduction we need to understand. Solid are the best conductor. Solids are best conductor and poor insulator. Okay, so the conduction mostly take place in solids. Okay, solids conduct heat by conduction. Now you can see this animation now. Look at this animation now. Watch this animation now. Okay, so you can see here now what is happening here. Just observe this one. Okay, now what we need to understand is that this end is the hot end and this end is the cold end. What we observe is that energy transfer from this side, energy transfer from hot end to cold end, energy transfer from hot end to cold end. So hot end to cold end by vibration of atoms, in this case by vibrations of atoms. So as you have seen in this animation, these molecules absorb thermal energy. When they absorb thermal energy, their kinetic energy increase. They start vibrating, but there are strong intermolecular forces between them. So you can simply understand like a spring. So the strong intermolecular forces, we can simply imagine that are like spring actually. These are molecules or atoms. So if one start vibrating, it will transfer its energy to the next one, and this process continue until the energy reach at this point. Okay, so the energy is transferred in this case by vibrations of atoms. Okay, vibrations of atoms. So now here, how does heat move through solids? You have to say conduction. This process is called conduction by vibrations of atoms. What happens to the particles when they are heated? So you will say they vibrate faster. More thermal energy we give them, they vibrate faster because they have higher kinetic energy. But air, for example, air does not conduct heat very well because air molecules are apart from each other. So these points we have to understand. Okay, so these points we have to understand about conduction. So this is okay? How energy is transferred in this case? Is transferred by vibration of atoms. And this method is very useful in solids. But this is not very good in liquids and also not very good in gases. Okay, so this also we need to understand. Okay, next one please. Now here you can see now this is another example for you, so we can simply understand from here. This is a rod actually, so you can see in a different way. So you can see the atoms inside now. So these are the atoms. If you look at this one, this atom is vibrating like this, means from here to here, so it's vibrating here. So you can see vibrating here. But this one, you see, it's just vibrating this much. Okay, it's vibrating here. So we can say that this end is a hot end and this end we will say is cold end. So this higher energy, lower and lower. Okay, so this is how energy is transferred by vibrations of atoms. Now let me ask you one question now. Let's say we have this rod now. Let's say this temperature of this end is equal to 100 degrees Celsius and temperature of this end, let's say, is 0 degrees Celsius. Let's say this is rod A and we have another rod here. This is also made of the same material, but we give it name rod B. Material is the same. Now let's say this end is at 100 degrees Celsius, but this end is at 40 degrees Celsius. In which case heat will flow faster? In rod A or in rod B? You have two rods, they are made of the same material. One rod, one side temperature is 100 degrees Celsius and other side temperature is 0 degrees Celsius. And we have rod B, it has 100 degrees Celsius on one side and other side has 40 degrees Celsius. So in which case heat will flow faster? Means the heat transfer is faster. So the question is that in which okay, this one please. You need to understand is that heat transfer faster is if temperature difference is bigger, big temperature difference. So let me ask you this one another way. Let's say you have rod here now. This is at 100 degrees Celsius. It has to be A actually. Let's say this is at 100 degrees Celsius. If you place another one that is also at 100 degrees Celsius, in this case heat will flow or not? If two rods, they are at the same temperature, there will be no net heat flow. Okay, so this one please you need to understand, if temperature difference is greater, heat transfer is faster. Okay, so you can look at this example now. If two rods, they have the same temperature, there will be no net heat flow. Now, let me ask you in a different way now. Here, let me give you another situation. Let's say we have this rod like this. We have a rod like this. Let's say this side temperature is 100 degrees Celsius and this side is 20 degrees Celsius. Now I take this rod now, I place in a vertical direction now, in this orientation now. Now this side has 100 degrees Celsius and this side is 20 degrees Celsius. In which case heat transfer is faster? Let's say this is case 1. Let's say this is case 2. In which case heat transfer is faster? Heat transfer is faster. Heat transfer faster. Is it in case 1? Is it in case 2? So you have to look at this cross-sectional area here. So is it case 1? Is it case 2? In which case heat transfer is faster? Excellent. It has to be this case 2 actually. Because cross-sectional area, if it is larger, heat transfer is faster. Okay, so one thing you need to understand, the thermal energy transfer increase if temperature difference between two ends is greater, between this end and this end. If temperature difference is greater, heat flow faster. And the second thing you need to understand is that heat transfer also depends on cross-sectional area. So if this cross-sectional area is larger, heat will flow faster. Okay, because in this case molecules only here, this distance is small, so heat transfer will be faster. In this case, heat transfer will take longer time. If they are at the same and temperature is the same, in this case it will take longer time. In this case, heat transfer will flow faster. So these 2 points we have to understand. I have written for you: one, temperature difference higher; second, cross-sectional area is larger. Thermal energy transfer will be increased. So I will also send you this slide. So this is what you need to understand. Okay, next one please. This is a beautiful animation for you. So you can see now, this is in metals. So you can see now, this is in metals. How heat flow in metals. So we heat up this and you see the molecules vibrate, and also due to movement of electrons, because electrons have, metals have free electrons. So metals, we call them, they are good conductors. Why? Because metals have free electrons. So metals have free electrons. So metals have free electrons. So these electrons, they will also carry energy from one end to the other end. So in metals, energy is transferred due to vibrations of atoms. So you will say vibrations of atoms. One thing, due to vibrations of atoms. The second, due to free electrons. So the metals are very good thermal conductors because metals have free electrons. Okay, so this is how heat transfer takes place in metals. You can see how energy is transferred from one end to the other. Okay, so this is what is happening in metals. So metals are good thermal conductor because they have because in this case energy is transferred due to vibrations and also due to free electrons. Okay, so this is what we need to understand. Okay, next one. So here please, this is what we have seen now. We have seen how metals conduct heat. So metals conduct heat because, one, due to vibrations of atoms, mean these atoms, they will vibrate. The second, due to these free electrons. Okay, if we heat from here, these atoms, electrons will go this side. Okay, so they will carry energy from here to the other end. So they are free to move. So they are free to move. So this is, these atoms then vibrate like this. Okay, so this is how heat energy is transferred in metals. Okay, here please. Now this is the key point until now, what we have discussed now. So we have discussed conduction take place in solids. So you have to be very clear, conductions mostly takes place in solids. Conduction takes place in solids. Why? Because molecules are close together, atoms are close together. And best conductors, solids are better conductors and poor insulator. Gases are poor conductor but good insulator. Okay, because in gases, molecules away from each other, so the energy cannot be transferred due to vibrations. So the gases are poor conductor but solids are best conductor, liquid between them. So when heated, temperature will rise, kinetic energy of particles increases, vibrates more about fixed positions, and they collide with neighboring molecules and pass energy to them. So this is how energy is transferred in solids by conduction. So these are the points you have to be quite clear. So I will circle this one. So you have to be clear about this one. You also need to understand best conductor and poor conductor. Okay, so vibrations of particles, no net flow of medium particles, means atoms do not move actually in solid from one side to the other side. Okay, so you have to be very clear. No net flow of medium particles means no net flow of atoms. So here, when to use actually conduction to explain. So we use conduction when we talk about good conductors, or we talk about poor conductor, or when we talk about air. If the air is present, if air is present, then we will say heat flow will be slower because air is poor conductor and air is gas, molecules away from each other. So in gas we will simply say that molecules away from each other, molecules away, okay, away from each other. So this is, we need to understand, that's reason air is not good thermal conductor, air is a poor conductor. Okay, so heating element and water, when two mediums are in contact, so heat is transferred by conduction. For example, it means that, let's say we have boiling water inside. Let's say this water is boiling. I will say this water is boiling water. Okay. If you touch this one, let's say you touch this. Let's say this is your hand. If you touch with hand, you will feel this is hot. So in that case, energy is transferred by conduction because you touch. So when you touch something, you feel that is warm. In that case, energy will be transferred by conduction, by contact. So we can also understand energy in conduction is also transferred by contact, by contact, when you touch something hot. So this is also we need to understand. Okay, I hope these things are clear, and also I will send you this slide. Okay, so are these points clear, how heat transfer takes place in solids? Okay, excellent. So let's go to next then. If this is clear, wonderful. Let's try to understand this one now. Okay, so before I explain to you, we need to understand what is conductor. So we need to understand is that what is conductor. Okay, so we need to understand what is conductor. So conductor, we can simply define that material that can conduct heat, can conduct easily. So this is very important. Conductor, when we define, we say a material that can conduct heat easily, can conduct heat easily and quickly. So if you wanna write down quickly as well, we can also write down quickly. So these two things are very important, easily and quickly. Okay, now let's say we have, this is one material, this is one rod, this is made of this material. We have an other rod that is made of an other material. So this is also one rod and this is also an other rod. So we can, this is small object. In this case, we are saying this one is a drawing pin actually. Small pin actually. Let me sketch this. Look like this one. If you see this one physically, this will be something like this one. Okay, so this is drawing pin actually. If you like drawing, maybe you have used this one sometime in your life. So this is drawing pin, it look like this. Okay, so this is drawing pin. So we attach here with wax. So we use wax and we place this one at this point. And we also place one here. You can see the same drawing pin here and also same here, and the same one we also place here now. Now, one thing we have to be very clear is that the distance from the source, let's say I say this distance, let's say this distance from center, also I can take distance from the center to center, but I'm just taking from here, I'm saying it has no size actually. So let's say this has distance d1, and this distance center to the end, you can say, let's say this is d2 in this experiment. So this distance has to be the same. So let's say this is d3, and also we can say, let's say this distance from here, let's say this is equal to d4. So in this case, d1 is equal to d2, and this is equal to d3, and this is equal to d4. Okay, so this is a source of heat now. So now when we switch on this one, let's say we switch on the source of heat. We switch on this source of heat. So what we noted is that after 73 seconds, when we switch on this source of heat, this fall down. So this will fall down. And then we noted that after 125 seconds, first this fall down, then this fall down, and then we have brass, this fall down. I can say this is third one, and this one is fourth one. So now you have time is given to you. Now you can see this took only 73 seconds. For heat to flow from here to here, time taken is only 73 seconds. Heat to flow from here to here, time taken is 125 seconds. And here time taken is 189 seconds. And heat to flow from here to here, time taken is 340 seconds. So you need to understand in which case heat is flowing faster. Mean heat is transferred quickly from here to this drying pin quickly. So in which case it has been transferred very quickly. So you will say that is copper. So copper among these material, copper is the best conductor. The second one will be this, and this will be third one, and this one will be fourth one. Because time taken is shorter, it means heat flow faster. And so time taken is shorter, so I will say time is shorter, heat flow faster. So we will say heat transfer faster. So we will say heat transfer faster. So that one is the best conductor. So in this case, best conductor is copper. So this is the best conductor. Okay, is this point is clear to you how to decide which one is a better conductor? We can do this very simple experiment. We can have a source of thermal energy and we can place like this and we can find out which material is the best conductor among those materials. Yeah. So is this okay now? How to find out which one is better conductor? Okay, excellent. So if this is okay to you, okay, excellent. So if this is okay, so we can move on to next one. Okay, now please, here is another experiment for the same purpose. Now you can see here, we can also do this experiment like this now. You see, we have arranged this one. We have a source of, this is heat source, a source of heat. So this is a heat source is here. We have these 4 rods now. And we have these metal balls actually. So these are small metal balls. In this experiment, we are placing small metal balls and we are using wax actually. With wax, we attach here like this. 5 balls here, 5 balls here, 5 balls here. Now, let's say these 5 balls, they fall down. Let's say they took time for these 5 balls to fall down. Time taken, let's say, is equal to 10 seconds. And for this one, time taken for these balls to fall down, let's say, is 20 seconds. And for this one, let's say, time taken is 25 seconds. And for this one, all these 5 balls to fall down, time taken is 40 seconds. So let's say this is 1, this is 2, and this one is 3, this is 4. So which rod is the best conductor? So which one is the best conductor? Is it 1, is it 2, is it 3, is it 4? So which one is the best conductor? So 1, excellent, because you see in one these 5 balls, they just took 10 seconds to fall down. It means heat flow from here to here very fast in a short period of time. So this is the best conductor. 1 is the number 1. Okay, because it flow very fast. That one is the better conductor, or you can say the best conductor among these 4 rods. Excellent. So let's go to next one. Now you see here, please. Read question and then tell me the answer. Okay, here please. Try to answer this one now. Okay, so let me, okay, very good, good conduct. Let's say this one, this is metal, this one is metal. Conductivity, excellent. So metal, let's say this is at 20 degrees Celsius, 10 degrees Celsius, so it's colder than your body, for example. And the piece of wood actually, this is also at 10 degrees Celsius, and this is wood actually. But when we touch them, okay, when we touch them, this you will feel is colder actually, and this one you feel is warm. It is good conductor. You can simply say metal is good conductor. So this is a simple way to say that it is a good conductor. But the reason to little explain more is that excellent, the conductivity of metal is better. That is excellent. So we can simply say that if my body is at higher temperature, let's say this is at 37 degrees Celsius. So what will happen? Heat will flow from my body into this one very fast. So my hand will lose more heat. So my hand will lose more heat. So you will say hand will lose heat faster, so you will feel cold actually, lose heat faster, so we will feel this one is colder. But in this case, this is 37, but this is also at 10. Heat flows slowly because this is a bad conductor. Heat flows slowly, so we don't feel that cold because our hand will not lose heat very quickly, so we feel this is warmer. That is the reason. Okay, so this is how you can explain. Here, please. Okay, so because in this case your hand will lose heat quickly, so you feel this is cold, and this one you feel is warm because your hand will not lose heat quickly. Okay, so this is what we need to be very clear. Okay. Okay, next one. Okay, now let's do this simple experiment now. Now we will look at this experiment now. in this experiment, you can see here, we have a cube of ice. So this is ice cube. We place at the bottom. This one is a tiny ice cube. You can see here. So maybe color contrast is not good. Some student maybe not see very clear. So now it is very clear now. So this is the ice cube we place at the bottom, and this is to simply hold this one so it cannot go up. So at this point we start heating now. So you see the water is boiling here. You can see the bubbles of water. If you look at closely at this one, you will see there are water bubbles here. But this ice is not melting. Here it means temperature is different than temperature. Here I can say if this is, let's say, is 100 degrees Celsius, ice is not melting. So I simply can say this temperature is still 0 degrees Celsius. So you can see the heat doesn't flow from here to here very fast. So we can say that water is poor conductor. So what you can conclude from here? You can say water is poor conductor. Okay, poor thermal conductor. So heat doesn't flow from here to here very fast. Okay, so this is we can conclude from this experiment. Okay, so we can also do this demonstration in classroom. So water will be boiling here, but ice will be staying at this point. Why? Because water is poor conductor. Okay, here please. Try to answer this question now. Okay, please read question and try to answer. Okay, excellent, excellent. So answer is B, excellent. So okay, so this is the answer, excellent. Okay, excellent, excellent. So let's go to next one now. Next topic is about convection. So we have discussed about conduction now. So next topic over, we will discuss about convection. We will discuss convection. So conduction, for example, we have discussed is conduction takes place in solids. Why? Because molecules in solids are close together. So conduction is better way for heat transfer. But now next we will talk about convection. Now convection takes place in fluid. So we need to understand convection takes place in fluid. So the fluid means that it takes place in liquid and also it takes place in gases. Okay. For example, you can see here, this is our heat source. You can see this one is heat source. I will just discuss the main idea of convection and then we go to radiation. So convection we have discussed in class one time. I also taught you about convection. So we will go faster. So first of all, the warmer fluid at this point, it will rise. Warmer fluid, first of all, here you can say expands. You see, warmer fluid expands if heating. So when it expands, its density decrease. When the density decrease, so we will say it is less dense and it will rise. So means the hot fluid from here, it will rise. So this is the hot fluid. So hot fluid rises. So why rises? Because its density is lower. Hot fluid rises. Simply we will say because it is less dense. So hot fluid will rise, less dense. And at this point, the cold fluid is denser. So we will say the cold fluid on this side. So we will say cold fluid sink because cold fluid is denser. So we will say cold fluid sink. So you have to understand sink and rise. Why? Because this is denser fluid. Okay, and this process continue. So the cooler fluid, denser, contract if cooling and sinks, creates a convection current. Convection current simply means that this is kind of circle, you see, it formed like this. This is called convection current. Means hot fluid is rising, cold fluid is sinking. So this form kind of circle. So or we can simply say this path. This is called convection current. Okay. So in this case, density changes, net flow of medium particles. In this case, this particle absorb heat from here. It will go from here to this point. But in case of conduction, there was no net flow of particle. So this is the main difference between these two. So in case of conduction, there was no net flow of particles. But in case of convection, you will see there is net flow of particles. So this is very important. You need to understand. Okay, so in this case, density changes and net flow of medium particles. Medium particles means this is made of water. We have water inside. So the water is a medium in this case. So in this case, water is a medium. So water molecules, they will move from hotter place to colder place. Okay, so water is medium in this case. Okay, so this is what we need to understand. Okay, please, any question about this one? Until now, do you have any questions? So this is the main idea behind convection. Okay, excellent. If it is until now, if it is clear to you, that's wonderful. Okay, that's wonderful. So just see what this animation now. That's all then for today. Okay, excellent. Here, please. Watch this animation. So this is what you can see is happening in convection. Okay, so the last thing you need to understand is this. How to define convection current, that's all. Convection current, we have discussed this cycle, this path you can see, the closed one, we call this is convection current. So this is what we call is convection current. So this is convection current. So you need to understand is the path taken by rising hot fluids and sinking cold fluid. That is called convection current. So you need to be able to define this one. You need to be able to tell someone what is convection current. So this is how you can tell someone. Rising hot fluids and sinking cold fluid. That path you can see are disclosed here. Okay, so this is convection current. Okay, so that's all for today's class and I will send you homework later. So see you in next class. If you have any questions, you can ask me now. Otherwise, our class is over. Okay, so then bye for now and see you in next class. Okay, bye for now. Next class we will finish this thermal physics. Next class will be the last class. Okay, bye for now. Bye.